Hi guys, welcome to section 5.1 and actually welcome to chapter 5. All right, so we're switching directions. The last previous chapters we were looking at the derivative, and now we're going to be looking at the opposite of the derivative, and the opposite of the derivative is called integral. All right, and we're going to explore some applications of the integral, and we're going to see how they relate back to the derivative. Okay, so just like we started the discussion on the derivative with the tangent line and velocity, in section 5.1, we're going to be looking at some applications of the integral, and we're going to see that the applications of the integral are areas and distance. Areas and distance versus tangent line and velocity. Okay, so on one of the very first sections we did together, we talked about this area problem. One of our very first discussions on the an introduction of calculus, what is calculus? And we talked about how back in the day they wanted to estimate a circle, and they did it by shapes, right? Because we know how to calculate the area of these straight edged shapes, but curves are more difficult, right? So we could estimate it with a triangle. A more accurate estimation would be a square. An even more accurate estimation would be a pentagon, right? And we can keep going and going and going. And then we can have a 1, 2, 3, 4, 5, 6, 7. That would be even more accurate. And essentially, a circle, we can think of that as a polygon with infinitely many sides. So we said, and we've discussed before, how we can estimate the area of the circle by taking the limit as n goes to infinity of a to the n. And then that equals, we'll just call it a for area, okay? And we're going to take a similar approach, not for circles, but for curves. Okay, so if we had, and remember, we could do straight curves, no problem, right? Because that's just a whole bunch of rectangles we would have to find the area of and add them up. So the straight, here, let me do my eraser. The straight curves aren't the problem. We can find the area under those. It's the curvy ones, all right? So something like this. So this would be our f of x. All right, and then the problem is, how could we find, let's say we're going from A to B, how can we find the area under the curve from A to B? Okay, we can call that area S. So how are we going to estimate that? Okay, so this is the problem. We want to now be able to find the area bounded by the curve y equals f of x, and then these boundaries, right? So essentially this is the boundary x equals a. Then we have another boundary, x equals b. And then our last boundary is the x-axis. And our approach is going to be something similar to what we did with the area problem. So let's write that down. So we're going to approach this problem. We approach the area problem in a similar way like we did to find the slope of the tangent. So let me remind you how we found the slope of the tangent way back in the day, before we knew it was the derivative, before we knew how to take the derivative. What we had to do is we approximated the slope. Remember how tedious that was? we approximated the slope by using slopes of the secant line. Okay, so if you recall, and hopefully you remember because it wasn't that long ago, if we wanted to find the slope of this tangent line at A, our approach was to choose another point, we call them P and Q, and look at the slope of that tangent line, and then we moved Q towards P, and eventually that secant line in green would become the tangent line. Okay, and what that process is a limit. So we took the limit of those approximations. And we're going to do something similar to figure out the area. All right, so how that process that we used for the tangent line, we're going to now use for the area under a curve. So what we're going to do, we're going to approximate the area under the curve using rectangles, because we know how to find the area of rectangles. So we will approximate the area under a curve using areas of rectangles. And then we'll take that limit again. And that process, and let me back up. Remember this process in orange? This was finding derivatives, right? That was the slope of the tangent is finding derivatives. Finding area under a curve by using rectangles and taking that limit is the other branch of calculus. It's integral calculus. So that's where we're at right now in this process of calculus. We're in integral calculus now. So to demonstrate this point, let's use a real example. Let's use a function sine of x, and we're going to estimate the area S from x equals 0 to x equals pi over 2. And how many rectangles are we going to use? We're going to be using 4 rectangles. Okay, because that's how we approximate area. We look at rectangles. Okay, so we're going from 0 to pi over 2. And if you want, just kind of remember what our sine curve looks like. That happens at pi, and this happens at pi over 2. Okay, so sine of pi over 2 is 1. And we're looking at maybe something like this, okay? And then again, this is y equals sine x. Okay, so they're telling us to use 4 rectangles. And there's different ways to calculate. Oh, I'm sorry. Let me do one more thing. We want to find this area under the curve above the x-axis. All right, so a similar thing of how we solved it before. All right, and we're calling that S. So to approximate S, we're going to use 4 rectangles. How we create the rectangles, we can create them in different ways. How I'm going to create them right now so we can get something systematic and get some formulas going. I'm going to divide 0 to pi over 2 into 4 even widths for 4 rectangles, right? So all my rectangles are going to have the same width. And then let's see. So pi over 2 divided in half is pi over 4. So that's half of pi over 2. And then pi over 4 divided in half is pi over 8. So each one of these notches represents pi over 8. So there's 1 pi over 8, 2 pi over 8, 3 pi over 8, and then 4 pi over 8. Okay. And then we're going to create rectangles. Maybe we'll create rectangles that look like, I don't like that. That look like this. So we can maybe use this rectangle, or maybe use a rectangle that looks like this, or we can use a rectangle that looks like that, or one that looks like this. Okay, so for now, it doesn't matter what type of rectangles we're going to use because they don't give us any instructions. But there are some particular types of rectangles. There are some type of rectangles that use the right endpoint to determine the height. And then there are some rectangles that use the left endpoint to determine the height. All right, so let's write out. Those are actually definitions. That notation appears in your textbook and your homework. So for instance, let's say our 4 rectangles have even width. So in our case, that width is pi over 8. And then they'll use the right endpoint for the height. To determine the height of each rectangle. That notation we use, we're going to use R for right, sub 4 for 4 rectangles, okay? So a picture of that. Luckily, this curve isn't too complicated, so we can recreate it relatively quickly. There's pi over 4. There's pi over 8. There's 3 pi over 8. Okay, so even width, that's the first part. And then the right endpoint determines the height. So for instance, at pi over 8, we would use, let's write our function, f of pi over 8, or sine of pi over 8, that's going to be the height. So this is the first rectangle of R4. And then the right endpoint of pi over 4, we would map it to the graph, and that's going to be our height. Map 3 pi over 8, and that's the height of the third rectangle, etc., etc. All right, and so in this case, we can call it, so we can call this S1, area of the second rectangle would be S2, etc., etc. And now we're saying if we add up all those rectangles, that's going to approximate the area under the curve of sine of x from 0 to pi over 2. All right, so what is that going to be? Then R4, let's figure out the area of this first rectangle. Well, we know the distance is pi over 8. So it's going to be, length times height, or width times height. So we're going to be pi over 8 is this distance. And now what's the height going to be? Well, it's going to be sine of pi over 8. So that's your S1. And then S2 is something similar. Again, this is distance, this width is pi over 8. And then the height of this rectangle is sine of pi over 4. So that's your S2. And we're going to keep going. S3, the width is pi over 8, and the height of your rectangle is sine of 3 pi over 8. And then last one, I think I have one more color. Same thing, pi over 8 is the width, and then the height is sine of pi over 2. Okay, there you go. And another thing too, determining that even width, we could kind of just eyeball it, or we did eyeball it, but if the numbers were a little bit more complicated, you can always take the distance of the interval you're concerned with. So distance is a subtraction problem. So pi over 2 minus 0, and then we're dividing that into 4 equal pieces. So each piece is going to be pi over 8. Okay, so we can also go about it a little bit more systematically. All right, and then final thing, if we were to look at all of these rectangles and add them all up, we're saying it estimates the actual area under the curve, but is it going to be a smaller estimation or is it going to be an overestimation? In this case, it's going to be so it's going to overestimate in this case. Not all cases, right? If it was a decreasing function, it could underestimate. All right, but in this case, R4 is overestimating S, the actual area under the curve. Okay, so that's how we would calculate R4. What do you think L4? What do you think L4 would represent? It would be 4 rectangles of equal width. Height is determined by the left endpoint of the rectangle. So a similar definition. Okay, so again, we can quickly sketch out our curve. Luckily, it's not too complicated. Equal widths, just as before. Okay, so in this first one, our first rectangle, this is our endpoint. So that rectangle just has a height of 0. And in our next rectangle, here's our left endpoint. So we're going to use that height on the graph for our rectangle. All right, so this is going to be S1, S2, and then S3 uses the left endpoint, so pi over 4 on our graph. That's your S3. And then finally, left endpoint of the fourth rectangle is 3 pi over 8. And that's your S4. All right, and in this case, again, we're saying that if we find the areas of all these rectangles and add them up, that's going to approximate the area under the curve. And in this case, do all those rectangles overestimate or underestimate? And in this case, it's an underestimation. All right, and that's not always the case. For instance, if it was a decreasing function, it would be a different story. All right, but we're just going to note that it's an underestimation. Okay, so what is L4? All right, well, we're going to add up all of the rectangles. So this first rectangle is just 0. All right, but we can also, multiply by the width of that rectangle. And then the height is sine of 0, which is 0. Okay, and then next up, this rectangle right here, the width is still pi over 8, and now the height is sine of pi over 8. All right, so that's the area of that one. Okay, and then we have the third rectangle, so the width is pi over 8, and the height is sine of pi over 4. And then finally, I forgot to shade it in. Finally, our fourth rectangle, we have the width times the height, which is sine of 3 pi over 8. And, you know, we could throw that in our calculator and we could figure out that estimation for S. All right, so what we've discovered, we said L4 was an underestimation of S. So L4 is less than S, but R4 was an overestimation. R4 was bigger. So we have this three-part inequality. All right, so the actual curve is between L4 and R4. And now, how can we relate this back to limits? Well, what would happen, let's bring back our curve. What would happen to L4 and R4? Or I shouldn't say L4 and R4. What would happen to our estimation if we didn't use 4 rectangles, but we use like 1,000 rectangles? We would get a better estimate. So that's where we're going with this limit idea. We're just going to keep on creating more and more rectangles to get a better estimate of the area under a curve. All right, that's not even 100, but you guys get the gist. All right. So now again, just imagine what would happen if it was like R1,000. And what's going to happen is we're going to let this n right here go off to infinity. And I used the wrong notation, so let me erase the R and put an S, okay? And now all these rectangles are going to get closer and closer and closer to the curve the bigger R gets, okay? So what we're going to see is that the limit as n goes to infinity of ln is equal to the limit as n goes to infinity of r sub n. And this is going to equal S. That's going to equal S. All right, so what's that actually going to look like? Well, first of all, let's get the width of each one of these rectangles. I'll just draw it over here. And we can do, let's say this is a left-hand limit. Well, we know that each rectangle is going to be base times height, right? Well, the base is, remember, we're going to take the total length of that interval, so pi over 2 minus 0, and we're going to divide it by the number of rectangles we have. All right, so the base of all of these rectangles is going to be pi divided by 2n. Okay, so we're going ln, it's a infinitely long sum, and we're going to start with our very first rectangle. So there's the base. And then if we use the left endpoint, we're going to start at 0, right? So that's your first rectangle. And now the second rectangle is going to start b away, right? Or pi over 2n. Just like right here, when we had 4, the next rectangle started at pi over 8, the distance, the width of the rectangles. And then the next square started at 2 copies of pi over 8. And then the next square started at 3 copies of pi over 8. And then the last square happened at 4 copies of pi over 8. So we can determine the left endpoint by looking at multiples of the base. Multiples of the base. So for instance, your next left endpoint is going to be the starting point plus one base of the rectangle. Okay, and then the third rectangle, the area, there's the base times the height, and the left endpoint is going to be 2 copies of that base of the rectangle. All right, and we're going to keep going because this goes on forever, right? Until we can just call it n. So there's the base of the rectangle, and then the height on the nth rectangle is going to be the left midpoint. And at the nth rectangle for the, here we can look at this, L4. Let's see, in this case we had 4 rectangles, and the last endpoint we used was 1, 2, 3 bases when there was 4 triangles. So it's going to be 1 less, plus n minus 1 bases. Okay. So we are going to introduce, so we have this pattern. There's definitely a pattern in this sum, right? The thing that's changing each time, let's see, that stays the same. The things that's changing is how many copies of the base, right? And it's very systematic. It goes 0 copies of the base, 1, then 2, then 3, then 4, then 5, all the way up to n minus 1. And so when we have patterns in sums, we can use summation notation. Summation notation. And then I'll introduce the notation just using an example. It uses a capital epsilon, looks like a fancy E. And then we always have where we're starting. Let's say we're starting when n is equal to 1, and we're going up to n equals 5. All right, and then in this case, we can just add together n. And so we're going to add this argument n as n varies from 1 to 5. So n equals 1 plus n equals 2 plus n equals 3 plus n equals 4 plus n equals 5. Okay, so that's our thought bubble. It doesn't really relate what we're doing. That's just a previous definition. So using that summation notation, let's talk about L sub capital N like this. We're going to use summation notation. We start when n is 0, and we go all the way up to n minus 1. Okay, and we're already using n, so let's introduce a new variable. We'll call the counter I. So we're going to go from 0 to n minus 1, right? This is 0, this is 1 copy, 2 copies, all the way up to n minus 1 copies. And what we're doing is we're adding this same thing over and over again. The base of the rectangle times the sign. Our starting point is 0, and then we're adding copies of pi over 2n. We're adding copies of the base. Okay, and it's going to go all the way from 0 to n minus 1. And you don't have to write the 0 there, because when we add 0, it doesn't change anything. Okay, good. So that's ln. And then Rn is something very similar, except we're using the right endpoint. And so how that's going to change everything, and I'll just go back up to our simple example. L1, we used 1 copy of the base. For the first rectangle. The second rectangle, we use the second base, right? So there's 1 copy of the base, there's 2 copies of the base, 3 copies of the base for S3, 4 copies of the base for S4. So 1, 2, 3, 4 bases right there. All right, so then R4, or Rn is going to be really simple, but our counter is going to start at 1, and we're going to go all the way up to n. And then it's the same formula. Okay, so we know that if we take the limit of both ln and rn, we're going to get S, which is the area under the curve. So I'm just going to choose Rn. I'm just going to work with that one. I could have chosen ln, but I'm just going to choose Rn. So now we're saying that the area under the curve is this limit as capital N goes to infinity of R sub n. Okay, so that means Ra is equal to the limit as n goes to infinity, and R sub n is that definition. So it's the limit of a sum, which is new. The limit of a sum. Okay, so that's how we can estimate the area under the curve of our sine function. Let's make it more general though. So now we know how rectangles can lead to that area. Let's look at something more general. So instead of sine, let's say our favorite, just f of x, y equals f of x. And then we'll go on the interval a to b. Okay, so we're going to get little n rectangles. So let's go from x0 to xn, and we're going to have n many rectangles in between. Okay, so this first point right here will be x1, then x2, x3, x4, x5, and then this is going to be, let's do in general. We can do xi in the middle, that will be the general. And then right before b will be x sub n minus 1. Okay, so we're going to have n many rectangles in here. The base of each rectangle, and we're going to say it's equal width, we're going to call it delta x, change in x. So the base of each rectangle, we're going to look at the total distance of our interval. So b minus a, I'll do that in a different color so they kind of pop. And then we're going to divide that into n many rectangles. Okay, so we have these little n subintervals. So this is how we're going to name all the points. Again, we're going to use the x's because it's a ticker, right? So this will be represented by x sub I at some point. And so x0 is the starting point. And then x1, we're going to add one copy of delta x. And then to get to x2, we have to add 2 copies of delta x. And then what do you think x3 is going to be? 1, 2, 3 copies of delta x. And we're going to continue this pattern. All right, let's focus on x of I because that's how we can make a formula out of everything. It's going to be a plus I copies of delta x. And then finally, x of n. And that's going to be b. And we can also think of that as a plus n copies of delta x. Okay? And so it also creates all of these little subintervals, right? So n subintervals, and the subintervals are going to behave as the base of our rectangles. So for instance, we're going from x0 to x1, then we go to x1 to x2, dot, 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 of course, and then of course we have xn minus 1 to x sub n. All right, so we have all of these subintervals. Okay, so again, what are we doing? Because it's getting crazy. We're trying to do a more general definition for area under a curve. All right, and more general is always a little bit more complicated. All right, but now that we've set all of this up, we can talk about the definition of area under a curve. So let's say that the area A, we'll call it capital A, of the region S that lies under the graph of F and then for now we're just going to focus on continuous functions. So we're going to want F to be continuous under the graph of the continuous function F is the limit of the sum of the area of the rectangle. That's a lot of ofs right there. Limit of the sums of the areas of the approximate rectangles in symbols, math symbols, it's a little bit easier. It's just A is equal to the lim as the rectangles go to infinity of Rn. And let's write in what Rn is. So again, the base of the rectangles we're calling delta x. And the height is determined by the first endpoint. Right? The height is determined by the first endpoint. So here's f of x1. And that's your first rectangle. And then we're going to look at delta x times f of x2. That's your second rectangle. And we're going to go all the way up to the nth rectangle. Excuse me, I should say the area of the nth rectangle. Okay, so we can write that what we just had in brackets using summation notation. So that's what we'll do. It looks like I is going to be going from 1 to n. We can say f of x of I. And even more particular, let's back it up. It is x of I, but x of I is this. So let's use that, right? Our starting point is A, and then we're adding I copies of delta x. So we'll write A plus I delta x times delta x, the base of the rectangle. And we even know what delta x is. Delta x is b minus a divided by n. So we'll make that substitution. Okay, and then that's what we have in general for the area under a curve. So we'll look at that. And then we could have, like I said, I just chose to use Rn. We definitely could have used Ln. So I'll just write, it's also true. A is also equal to this limit if we were to use Ln. Okay, I'm picking on Rn because some nice things happen when you start this when your ticker starts at 1. So that's why I chose it. Okay, and in general, just to be clear, and I stated it a little bit at the beginning, we can use any height of the rectangle. So we can use any value of f within the sub-interval. All right, so we're still assuming equal widths, okay? And so what we call that when we use any value, not just the left or the right endpoint, that height in the ith subinterval could be, whoops, I forgot the notation. It's notated with the little star, okay? And so that would be the height of the ith rectangle if we don't use the left or the right left or right endpoint. All right, so, you can just do a quick sketch of that if you'd like. Looks like 1, 2, 3, 4, 5 rectangles. And again, you can use any value, right? Maybe we'd want to use this height. It's not at the endpoints, but it, fairly accurately measures the graph. All right, so it's kind of like a choose your own adventure type of thing. All right, so there you go. The largest height in the interval, if we were to use the largest height in the interval of for each rectangle, that would be called the upper sum. And then if we were to use the lowest point, that would be called the lower sum. So let's write those out. Let me get the precise definition. So again, if we chose the highest point in each interval, so if x sub I star is chosen to be the highest, then the sum is the upper sum. So it's the biggest overestimation. And then if we choose the smallest value in the interval, we would get the lower sum. Okay, so kind of an intuitive definition, but we're defining upper sum and lower sum. All right, so there you go. So using upper sum and lower sum, we can actually define that area A. So here's just an alternative definition for the area. Redefinition. Okay, so A, the area, is the unique number. There's only one that is smaller than all, keyword all, upper sums, and bigger than all lower sums. Okay, and I'm highlighting the word all because there can be infinitely many values between, an upper sum with 4 triangles and a lower sum with 4 triangles. But if we're saying all, that means we can have 1,000 triangles, we can have rectangles, 1,000,000 rectangles, et cetera, et cetera. So essentially it's we're looking at a limit again. Okay, so let's look at an example. We're going to number 22, and number 22 says, we're going to use the second definition to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. Okay, so the definition too is this one. When we're looking at the limit as n goes to infinity of r sub n. So we're going to find the area under the graph of this function, x squared plus the square root of 1 plus 2x, when your x is between 4 and 7. Okay. Excellent. So, it's helpful to draw a picture. You don't have to draw the exact graph, right? Because we all know how much effort it takes drawing a function. So just to get a quick visual, we have this function f, and we're going to be looking at the area between 4 and 7, and we're going to be looking at Rn. So we're going to create these even intervals and create rectangles whose height is the right-hand endpoint, okay? All right, so there's like quick drawing. This is taking longer than I thought. That's okay. Okay, so first of all, let's write out the definition of what this is, because then we can start reverse engineering and figuring out what we need to plug in. All right, and R sub n is the sum from I equals 1 to n of delta x, the base of each rectangle, times this. Okay, and that's something we established just up above, right, in this definition. That's this, okay? So I'm using this definition. We know the function, we know the starting point, we have to figure out delta. Okay, so delta x is going to be the distance of the interval, so b minus a, divided by n. So it's going to be 3 over n. All right, so just substituting that. So delta x is 3 over n, okay? We're going to be looking at f of a, but our starting point is 4. I is the ticker, right? We're going from I equals 1 to n of delta x, so 3 over n. Okay? So good. So we also know the value of f. F is x squared plus the square root of 1 plus 2x. So we're going to take this monster, 4 plus I times 3 over n, and we're going to plug it in as the input of x. All right, so that means the area, and remember the question doesn't want us to evaluate it. We're just setting it up, okay? We're expressing the area. It's going to be the limit as n goes to infinity of the sum, I equals 1 to n of 3 over n. And now plugging in 4 plus I times 3 over n to the function, we get this plus the square root of 1 plus 2 input. Okay, and there you go. And we can leave it like that because they don't really want us to evaluate it. They just wanted us to create an expression for the area. All right, so direct application of the definition. What we're going to look at next is going the opposite direction. So take a look at number 24. We're essentially going to be starting at this point, and we're going to have to work our way backwards to figure out the function and the interval. Okay, so we're doing the opposite of what we just did. So those words are determine a region whose area is equal to the given limit. Do not evaluate the limit. Okay. So again, we want to find the region, which means to find the function and the interval. That will describe the region. That's enough to describe the region. Okay, so the limit as n goes to infinity of the sum, I equals 1 to n, 3 over n again, times the square root of 1 plus I, 3 over n. Okay, well, we know, so again, they're expressing this area. We know that this is going to be expressed, the area is expressed as the limit of the sum, for Rn of course, of delta x times f of a plus I delta x. Okay, and I'm doing this just so we can match some things up. All right, so we can definitely see where the delta x is because it happens there and there. Okay, so we know that delta x is 3 over n. Okay, we can also kind of figure out where the starting point is. We have that up here, I of 3 over n, I of delta x is being added to the a. So we also know then that a is equal to 1. So that's good. And then the input, this 1 plus I 3 over n, is being plugged into what function? It's being plugged into the square root function. So we also know that f of x is just taking the square root of the input, which is just square root of x. So you see how we were able to reverse engineer that? The only thing that's left is to figure out your b. All right, the only thing that's left is to figure out b. Well, we know to find b, we know that delta x is b minus a divided by n, okay? So we know delta x is 3 over n, and we know that a is 1. All right, multiplying both sides by n, we can just cancel the n's. So b minus 1 has to be 3, so b has to be 4. So let's put everything together, right? You don't want a treasure hunt when you're having the solution. So that A represents the area or the region under the curve on the interval A to B, or 1 to 4. All right. So there you go. And again, they don't want us to evaluate the limit yet. We are going to start evaluating the limit in our next part.